So like I said, our learning target is to indicate whether the forward or reverse reaction is favored to reach equilibrium based on different disturbances. How are we going to reach this? Well, we talked about equilibrium yesterday. So we talked about equilibrium yesterday. Today, we are going to add some disturbances. Okay, and we're going to see that LeChatelier called that stresses. He's going to put some stresses in there. So how are we going to do this? What's our success criteria? To determine how changes in concentration stresses a chemical system. How changes in temperature stresses a chemical system. And how changes in pressure stresses a chemical system. Okay? So we're going to look at three different things and how it affects the chemical system. The pressure, the temperature, and the concentration. Now, LeChatelier's principle came from a man named Henri LeChatelier. He was a French chemist. He proposed that if a stress is applied to a system that is in dynamic equilibrium, the system will change to relieve the stress. So basically he says, if he stresses a system, the system adjusts to relieve the stress. Changes in concentration. He said that by adding a reactant, will always push a reversible reaction in the direction of the products. Now, how I think of this, folks, when I'm doing these, is I think that I have a teeter-totter. So, I'm going to draw a nice little teeter-totter here. That, if I'm at equilibrium, my reactants and my products were even, correct? So, for this particular problem, it said that I have added a reactant. So if I've added a reactant, isn't it going to cause my teeter-totter here to go down and my products here to go up? Absolutely. So what happens in the system is that the forward reaction produces more products in order to even it back out. So in this case, we would say that if we add a reactant, it's going to favor the forward reaction because we need to get more products to even out that teeter-totter. Does that make sense? Okay. Now, the next thing, I'm going to get my teeter-totter out of here because I'm going to put some words over it. The next thing says that if we remove a reactant, okay, so I take reactants away, what's going to happen to the teeter-totter? The reactant side's going to go up, the product side's going to go down, right? So what's going to be favored there? The reverse reaction. We're going to make more reactants. So the reverse reaction will be favored. The same applies to adding and subtracting, removing products. Okay, the same principle applies if we add or if we remove products. Temperature. Increasing the temperature causes the equilibrium position of a reaction to shift to the direction that absorbs heat. So, if I have this particular reaction right here, think of my teeter-totter again. If I add heat, what way is it going to drive the reaction? It's going to drive it to the reverse, correct? If I add heat, the heat side of the teeter-totter is going to go down. What if I take away heat? It's going to drive it towards the forward reaction. Now, this last one, I think, is the toughest, okay? This last one, I think, is the toughest. Changes in pressure. Excuse me. A change in pressure will affect the equilibrium of an unequal number of moles of gaseous reactants and products. So this is telling me that pressure only matters when I'm dealing with gases. Number one. Number two, it tells me that I have to have an unequal number of moles. What do I mean by that? Well, if I look at this equation right here, and I calculate my coefficients here, I see my reactant side has 3 and 1. So my reactant side has 4 moles of the gases. My product side has 2 moles of that gas. Are those unequal numbers? Absolutely. So pressure would affect this particular reaction. Now, how is pressure going to affect this reaction? Well, an increase in pressure causes a shift to the right because a decrease of pressure results when 4 moles of gas react to form 2 moles of gas. So basically, if I increase pressure, it's going to drive the equation to the smaller number of moles. Can I say whether it's forward or reverse? Not until I see the equation. Okay? So if I increase pressure, it drives it to the smaller number of moles. So if I decrease pressure, it's going to drive it to the bigger number of moles. Okay? Now we're just going to look at some of these LeChatelier's problems because I've got a little piece of paper here and I put it on this next few slides. Okay? If I look, it says, the forward reaction above is endothermic. The system is initially at equilibrium. In which direction will the reaction shift in each of the following situations? So we're going to answer. Our answers are going to be that it'll go to the forward, it'll go to the reverse, or it'll have no shift. Okay? Can be one of those 3 things. Forward, reverse, or no shift. So, it says that this is endothermic, the forward reaction. So if I got to put heat on this, where would heat be? On the reactant side, correct? Okay, just mental note that. If I add ammonia, where is it going to drive this reaction? Forward, reverse, or none? What do you think? If I add ammonia, it's going to drive it to the forward reaction, okay? Because think about it. My teeter-totter, right here is my fulcrum of my teeter-totter, okay? I add this, that side's going to go down, the product side's going to go up, so it's going to drive it to the forward, okay? The volume of the container is increased. Now, you might look at me and say, we never talked about volume. Okay? Which is a correct statement. We didn't. But if I increase the volume of the container, what's going to happen? I'm going to decrease the pressure. So when I decrease the pressure, what do I want to do? Okay? When I decrease the pressure, it drives the reaction to the number of moles that is higher or lower of the gases. Higher. Okay? So if I decrease the pressure, it drives it to where I have the higher number of moles. And which one is the higher number of moles? products. So which is going to be favored? Forward or reverse? The forward. Does that make sense? Okay, good. I add nitrogen. I add molecules of nitrogen. What does that do? Takes it to the reverse. If I remove hydrogen, drives this to the forward reaction. Temperature is increased. Remember, where did we say heat was? Where did we say heat was? On the reactant side. So I increase the temperature, will drive this reaction in which direction? Okay, well, where does we said heat is here, right? We said heat is here, correct? If I add heat, what's going to happen to my teeter-totter? It's going to go down, so what way is it going to drive it? Forward. Okay, forward. N2 is removed. N2 is removed. It's going to drive it towards the... What do you think, Code? Why would you be wrong? If I take away N2 right here, what way is my teeter-totter going to go? It's going to go up right here, right? So it's going to drive it to the forward. You're absolutely correct. Okay? Now, this isn't He, ladies and gentlemen. It's helium. Helium is added at a constant volume. Now, this is kind of confusing, ladies and gentlemen, because the textbook I got this problem from said that nothing will occur here because helium is not involved in this particular equation, which I get that. I understand that. Okay? But my problem is that if I add helium to that reaction chamber, what's going to happen? Okay? If I add helium in there, is my pressure going to be the same? I've got to be changing my pressure, don't I? So I'm saying that even though the book says that nothing should happen, okay, I'm saying that if I put helium into that chamber, I am increasing the pressure. If I increase the pressure, it's going to go which way? To the greater number of moles or the less? Lower, right? To the lower number. So what's the lower number of moles? 2. So it's going to drive it what way? To the reverse. That's my opinion. Okay, that's my opinion. Because I think that the pressure will change. NH3 is removed. What way? Reverse, right? Okay? We okay with LeChatelier's stuff there? Does it make sense? I hope. Okay.